All right, so you are starting with these handouts, and we are going to end up making a tab foldable. So what I want you to do is you are going to cut out around the black lines on each of your pages. Then you're going to put them in order. So the top is going to be the one that says trends of the periodic table, followed by the one that has atomic radius in the corner. After that, it should be ionization energy comes next. After ionization energy is electronegativity, and then ionic radius. So you're going to stack them on top of each other. Now this is after you've cut them out. I'm not going to take the time. Then you're going to staple them together along this dotted line, okay? Then you're gluing it into your notebook. I added a piece of duct tape along my turning edge just so that it's really nice and snug in there because it's a lot of pages. All right, so once you got your foldable assembled, you can go ahead and join me. We are going to start on the notes on the trends of the periodic table. We're going to kind of sum everything up. All right, so let's start with those 2 rules of attraction that we talked about this last week. Number 1, the bigger the charge, the stronger the pull. So in other words, the more protons we have in the nucleus, the more attraction there's going to be. And then rule number 2 was the greater the distance, the weaker the pull. So the further away from the nucleus our electrons are, the less attracted they are going to be. So we have this idea down here called effective nuclear charge, okay? An effective nuclear charge is the ability of the nucleus to pull in the electrons, okay? It's the ability of the nucleus to pull in the electrons. This is important because it affects all the other properties. So this is going to increase across a period because we're adding more protons. It decreases down a group because we are adding energy levels and we're getting further and further away from the nucleus, okay? So effective nuclear charge is the ability of the nucleus to pull in the electrons. All right, so that's really, these are 2 rules of attraction. It's going to increase as we add more protons across the row. It's going to decrease down the group because we're getting further away. All right, so let's review really quickly atomic radius. Remember that atomic radius is the size of an atom. It depends on 2 major things. Number 1, how many energy levels it has. Number 2, I can't do this. How big the charge of the nucleus is. So again, back to those 2 rules of attraction. How many energy levels it has is going to be how far our electrons are from the nucleus. How big is the charge of the nucleus? All right, so remember that atomic radius is the distance from the nucleus to the valence shell. More energy levels means we have a bigger atom. So this top part is really the most important part. I want you guys to label the trend on this periodic table. So we talked in class about the absolute highest atomic radius being francium over here. So it increases down a group, it increases as we go towards the left, and then if we're just looking at the periodic table as a whole, we're going to increase as we move closer to this corner. So the closer something is to francium, the higher its atomic radius is. And remember that it decreases across the row because the charge of nucleus increases, but the energy level stays the same. So remember we had that pull of the nucleus is pulling our energy levels more in. It increases down the group because we're adding energy levels and we're also adding nuclear shielding. All right, let's review our ionization energy real quick. Remember we said that an electron would be easy to lose if one of 2 things is true. Number 1, it is far from the nucleus. Number 2, the nucleus doesn't have very many protons. Okay, and again, this is right back to those 2 rules of attraction that we started with. If it's far from the nucleus, we have too much distance for the pull to be felt. And if the nucleus doesn't have very many protons, we have a little tiny magnet. We don't have a very strong magnet. So remember, the ionization energy is the cost in energy needed to remove an electron. And remember that no matter what, it always requires energy, even if the attraction is weak. This is an always situation. So there's always ionization energy. Again, let's go ahead and label the trend. We discussed in class that helium was the element with the highest value for ionization energy. Okay, So ionization energy increases as we go up a group. It increases as we go from left to right. It increases the closer we are to helium. Okay, so when you're trying to figure out, who's got the higher ionization energy, well, you ask yourself which one's closer to helium. Remember that it increases as you go from left to right because the charge of the nucleus increases. It decreases as we go down the group because we are farther from the nucleus. We're adding energy levels, we're adding nuclear shielding, so it's going to decrease. All right, electronegativity. This is new. We didn't talk about this last week, okay? So this is a new one, and this is kind of the really important one moving forward into chemical bonding, okay? So the pull of an atom on the electrons of other atoms, okay, so not on their own electrons, but on the electrons of other atoms, is going to depend on two things. How much positive charge is in the nucleus, and then, of course, how close is the nucleus to the valence shell? Oh my goodness, there's those two rules of attraction again. Distance and size. How much positive charge is in the nucleus? How far are we from the valence shell? So what is electronegativity? Electronegativity is the amount of attraction that an atom has for the electrons of other atoms. This becomes very important in chemical bonding because here we're talking about taking an electron away from another atom, okay? So things with a high electronegativity would be able to remove an electron from another atom. So this is related to the ionization energy. Atoms with a high electronegativity can take electrons away from atoms with a low electronegativity, okay? Now, this gets tricky when we get to the trend because there's one group that for once does not participate. Remember, this is about reactivity. This is how reactive it is. And our noble gases over here in group 18, they don't react with anybody. So they aren't given electronegativity values because they don't react. So the highest electronegativity is actually fluorine. Now, if this was ionization energy, it would go all the way to helium, but it's not. It's about attracting the electrons of another atom. And the noble gases don't do that, so they're out. But fluorine, in this case, is our highest because it has the highest ionization energy aside from the noble gases. But it needs one more electron to fill up its valence shell. So fluorine has the highest electronegativity value. All right? So electronegativity increases as we go up a group. It increases as we go from left to right. And it increases as we go closer to fluorine. So again, if we're trying to decide who has the greater electronegativity, it's going to be whoever is closest to fluorine. All right, and that takes us full circle. So what happens if they manage it? What happens if one atom takes another atom's electron or more than one electron? Okay, which is often the case. Now, if you look over here, the most likely is going to be our nonmetals. They're the most likely to go taking electrons. Whereas my metals over here are less likely to be able to take metals. They have low ionization energy, electrons. They have low ionization energies, so it is going to be much easier to remove one of their electrons than it would be for them to take one. Now, this also has to do with how many valence electrons they have. Metals have 1, maybe 2. Aluminum has 3, but that's about as much as you get. So 1, maybe 2. In order to fill their valence shell, they would have to add 7 or 8 more valence electrons to get that valence shell full. But if they just lose 1, they can drop down to a lower energy level. It's already full. Okay, whereas these guys over here, these nonmetals, they're already on this side of it. They have 4, 5, 6, 7 valence electrons. That's much closer to the 8 that they would need to fill up their valence shell. So these guys are going to be our takers. All right, so let's come over here and talk ionic radius. What happens when electrons are moved? Okay, so let's start with the situation with the metals. Metals tend to lose their valence electrons. They are going to drop down to an energy level that is already filled. Okay, the catch here is that now the number of positive protons is greater than the number of negative electrons. So that means we have a charge imbalance. So we no longer have a neutral atom. We have what is called a positively charged ion, or a cation. All right. So what about our other side of this? Well, the nonmetals tend to gain valence electrons until they fill up their valence shell. That's going to fill it up. So down here, we are getting rid of our valence shell and dropping down to one that's already full. Here, we're just taking the one that we have and filling it up. Now, if we do that, we're adding extra electrons. So now the number of positive protons is less than the number of negative electrons. That's going to leave us with an imbalance of charge as well. So this time we're going to have a negatively charged ion known as an anion. Okay? So now we got to talk about the trend here, the trend for ionic radius. So how big are my atoms? Well, first of all, cations, the metals, they tend to get smaller because they're losing an energy level. So they lose an energy level and they get a little bit smaller. Anions, the nonmetals, tend to get a little bit bigger. They're gaining electrons, and now we have more negative than we have positive, and so our positive protons in the nucleus are no longer holding on as tightly because they have too many electrons to hold on to. So cations tend to get a little bit smaller, anions tend to get bigger. But the trend for size is still the same as for atomic radius. All right, it increases as we go down towards francium. All right. So those are the trends of the periodic table you have to know. Are there a few others? Sure there are. These are the ones that we really need you to know as we move forward into chemical bonding.